So I will recall what we are doing. So we have been discussing quantum channels. Quantum channels are CP maps, which are trace preserving. That's all. Trace preserving is CP map. So for us, we may use different notation later. We may change the notation according to our communication protocols. So here for us, for the time being, we are just doing some sort of linear algebra and we are just doing the mathematics. So here, a completely positive map is sum from MNC to MMC, a linear map. And so if you have this map, then you can define this map on tensor P from MKC tensor M1C to MKC tensor MMC. And this is matrices of matrices. This is just MK of MNC. You can consider this like that. Okay. And from here to MK of MMC. And each entry is going to be a matrix. Here it's a matrix K cross K matrix. With each entry is a matrix there. Is a n cross n matrix there, which will the range will be K cross K matrix with. So each entry Xij is the matrix here, and that will go to P of Xij. And this you can write it like, I mean, yeah. So if we have for Mn, see for Mn, we have something called matrix units. Matrix units means we have one rank 1 operators, I, J. Okay, this is the notation. You can call it E, I, J or whatever. This is just, this takes, if you have any Xi in H, Cn, then this acting on I, this acting on that Xi is going to be just the inner product. The inner product, that will be a scalar, so the Xi will be like this. You just take it together, and then this is a scalar, you can bring it here. So which is just J, right, times I. It is this operator, rank 1 operators. Then these rank 1 operators, this is a basis for MKC. Okay? These operators with all Ij ranging from K to 1. Okay, it's a basis for MKC. This is actually orthonormal basis with respect to Hilbert-Smith inner product. We can see Hilbert-Smith inner product is just pointwise Euclidean inner products on MK square or something. So it is just the orthonormal basis for that with respect to the orthonormal basis. These are what are called partial isometries, and it's a, so this is partial isometry from the, I mean, vector, the vector corresponding to J, it takes to the vector corresponding to I. It is just the partial isometry. When J equal to I, it is a projection, one-dimensional projection. Okay, these are orthonormal bases. With respect to this, anything here or here can be written as some scalars, some Eij. I mean, anything here is, you take this Ij. This is an operator here. This is an operator in MKC, and you want to take an operator there, and you can just take it to be, I mean, it's Xij is a vector. I mean, you can take it to be you need an operator. Xij is a, I mean, Xij is a matrix. Not okay. I mean, Xij, when I write it like here, it may look like a scalar. It's a matrix entry. It is Xij is a matrix. Okay, where I mean, Xij is a matrix, or Xij is a matrix in MNC. So then you take the sum over Ij. Okay. This is just the matrix Xij in the ijth entry, and then everywhere else 0. Okay. So it is just the matrix with the ijth entry, it is Xij, and everywhere else 0. And then you sum over Xij. This is how any element will look like. Because this will give a matrix entry as Ij. Other things will give a matrix entry as other places. And you will get, I mean, this is how anything here will look like. Okay. So on this one tensor phi acting on this is just summation over ij times E of xik. Okay. And this will take it to a matrix in MMC, and that's how you get it. Okay. That's how it's different. I mean, that's how we get that. Initially, we are defining to be, tensor. Okay. Initially, we are just defining an elementary tensor like that, and that's how we extend it, and that's how we get it. So it is just the evaluation on all matrices. Okay. That is what this one tensor phi is. So CP means one tensor phi is CP means one tensor phi is positive. Okay. If A is in MK tensor Mn and A is positive, then one tensor phi is also positive. CP is equivalent to saying CP means, CP definition. By the way, CP means one tensor phi of this A is positive. Okay. A is positive, one tensor. It's a positive map of one tensor phi. This is what is called K positive, and it should be K for all K. It should be K positive for all K. Okay. So now we want to, so we saw some examples. One example was any endomorphism is any endomorphism from Mn to Mm, and not endomorphism, it's a star. So endomorphism is unto itself is what is called endomorphism. So any homomorphism, star homomorphism from Mn to Mm is CP, completely positive. And we had another thing is any map of the following form. If you have a V from MM C to MNC, then we can define phi of x equal to, for x in MNC, phi of x equal to V star will come here, V star x V. Right? V will take it from Mn to MNC, there x will act, and then it will get, V star will take it back. Okay? This is for all x in this. So this map, this is a map, this is CP. We have seen that. We have seen that this is a completely positive map. So this implies, I will do it there. So corollary to this, if V1 up to some Vk, Vd, let's say Vd, okay, Vd, or maps from, or in L of, sorry, here I have written something wrong. Don't say that. Correct me. Here it should be from Cn to Cn. Right? It's not from. Okay. It is a matrix of M cross N matrix. Okay. Okay. So all those things for L of Cm to Cn. Okay. It's a, or it is just the matrix M cross N matrix. It's just an M cross N matrix. Then that is, this is actually identified with M cross N matrix. Then phi of x in M and C equal to summation I equal to 1 to D VA star x VA is CP. So it's clear. If you have, it just follows, you have to prove that each one is, each one is CP. Then the sum is also CP. Sum is it just, sum has to take, and the one tensor phi will also look like that sum only. And the one tensor phi is also, it is just one tensor sum of that, you can take the sum out of the tensor. So it all reduces to saying that if you have some positive, positive operators A1 up to AN, sum of positive operators is positive. And that just follows from the fact that it is just sum of this. That you can take it, sum of that is also positive. That's all, just positive. Incidentally, in complex vector space, something is positive if A by AZ is greater than or equal to 0. This is enough. But actually in definition, in general, you will require that A equal to A star. Okay. And if you have seen it in functional analysis course, this for general operators, you don't need this. I mean, A equal to A, I mean, it should be self-adjoint and then it should satisfy this. That is what is positivity in real Hilbert space. For complex Hilbert space, we may define it like that, but self-adjointness is automatic. Because anything for any xi, if you have any A xi, this is real, will imply it is self-adjoint. Okay, that follows because of polarization identity. Okay, you have some polarization identity. So because of that, it is enough. I don't want to go through this. So, but we don't need this one more condition. It is enough to verify this. Okay, so because of that, it follows that it's CP. Okay, so the sum is also CP. Okay, but of course you should remember that polarization identity. Maybe I will write that polarization identity. This right? Summation 1/4, right? I power k x plus I power k y x plus I power k y, where k equal to 0 to 3. Okay. I think this is the correct, I don't remember. I mean, I don't remember, I didn't see recently. I think this is the polarization identity, which respects the inner product as norm. This is just the, I mean, same vector is there. It is like a norm. So this is the polarization identity. So if you use that, you will get that. It's an exercise. Using that, if it, I mean, if using that, if xi a xi is real, then it is self-adjoint. Then it satisfies xi a eta is equal to, is also real. I mean, this is also real, you can prove. Using this, if these are all real, then you can prove this is all, I mean, this is, I mean, you can take, this is real means you can take it, this is same as A xi xi. Okay? That will imply that this is also equal to A xi eta. You can prove using that. Huh? This is over C for X and Y in Z. Huh? No, there is no R. There is no identity as R. This is only for complex one. There is no such thing. So because of polarization identity, we only need that, and using that you can verify this. Okay. Now, so any such map is a CP map. Now we want to prove that every CP map will look like this. Okay. That is what is called Choi-Kraus theorem or Choi-Kraus representation. Okay. So the theorem. Okay, I will explain. I will state it and explain one by one. Okay. P is a map from MMC to MMC. Okay. So here the N is important. And 1, P is CP, completely positive. Then 2, this is equivalent to saying the following are equivalent. Okay, then the following are equivalent. Okay, this is the notation I use. The following are equivalent. This is equivalent to saying phi is N positive. It is enough, it is N positive. Okay. I mean, we have defined K positive. I mean, in that K, I mean, CP means it's K positive for all K. Here we are saying it is enough for K equal to N. Okay. Of course, for smaller things also it will follow, but bigger thing also it will follow. That is the, because we are working in finite dimension. It's important. That's why in finite dimension, these things will not be true. So these are all for matrices. So phi is completely positive is equivalent to phi is N positive. It is equivalent to saying phi of this. What is the notation? I'm just thinking. Pn, okay? Pn is positive, where, we'll write it here, where Pn is a, sorry, one tensor phi, sorry. One tensor phi of Pn is positive, okay, where Pn is equal to, this is in Mn cross Mn, okay, Pn is in Mn cross, so sorry, Mn tensor Mn, okay? Mn tensor Mn, and Pn looks like this, summation Ij. We have to, I mean, this just means that we are just specifying the an ijth entry as a matrix. Okay, tensor ij itself. Okay. ij equal to 1 to n. Okay. So we want to say this is about, I mean, this is a one tensor phi acting on here, one tensor phi acting on mn tensor mn. Okay, this is one of mn. Identity on one MNC. Okay. So this is a map acting on mn tensor mn, which are n cross n matrices. I mean, which are n cross n matrices with the entries being n cross n matrices. Okay. So you have to specify the ijth entry of n cross n matrices, and that is how it looks. This is the partial isometry corresponding to with j takes I to j, I to j. Yeah. I to j. Okay. So it is just this ij. I mean, sometimes I prefer to call it eij or eij. It's easy to write. This is okay, but this is the usual notation. This is the notation for us. So, okay, this is the Pn. Okay, so this Pn is greater than or equal to this one tensor phi of this Pn is, it is just n of this one entry is greater than or equal to 0. It is just clear why it is, because I mean any matrices xij is going to be, it's just I mean it's going to be linear combination of these kind of things. I mean you can see that from that it will follow. Okay, we will run the proof, it will be clear. Okay, then the fourth one is there exists V1 up to Vd, okay, from which are in MNC, of course, not MNC. Yeah, it will be in MNC, correct. No, it cannot be in MNC. It should be from MM, M cross N. Sorry. Yeah, that's what we have. Okay, such that P of X is equal to summation Vi star X Vi I equal to 1 to D. Maybe R, D is used for something else. I hope there is no confusion. If you want, we can change it. For the time being, let it be D. Okay, equal to 1 for all HC. So whatever I promised that is the theorem. Okay? Any phi of X will look like this. So this is the theorem we want to prove now. Okay? Of course, proof. 1 implies 2 is of course clear, and for 2 implies 3 only we need to prove that Pn, whatever that Pn is greater than or equal to 0. I mean, then phi of one tensor phi, I mean, by the definition of completely positivity, that is greater than 0. So we only have to prove Pn is greater than or equal to 0. Okay? So what is Pn? Pn should be greater than or equal to 0. So what is Pn? Pn is, for the time being, okay. If I write this, I get so much confused. Let me try it. Eij is easier for me. Okay. Let me write Eij equal to this. Okay. Ij. Okay. For here. I mean, I don't want to write each time this. I may get this arrows in the wrong way. Okay. Now this is easy. Eij tensor Eij. That is what is this summation over Ij. Okay. This is what is my Pn is. So if you take the square of this, okay, so Eij satisfies the following properties, which you can just, I mean, but the nice thing about writing it in this form is you can see those properties directly. It is just the inner product between j and I is 0 unless I equal to j. Because of that, it follows. I mean, it's very direct. Okay. Here we have to remember. E I K E L J is equal to delta of K and L E I J. It satisfies. It's just clear. You just compose those things. It's just clear. Directly it forms. Okay, because of that. Because of that, Pn is this, right? Eij, tensor Eij. Okay. So square, it will be summation over Ij. It is just this. If you, I mean, if you have Eij in that, the next one will square EKL or something. It will be only J equal to K will matter. Okay. So it is just going to be summation over Ij, summation over K. Otherwise, it's zero. Okay. In these two should be equal. Okay. So because of that, it will be K over E Ik EK Kj. That's what will come, which is Eij again. Okay. I mean, the tensor, the corresponding tensor will compose with the corresponding tensor, and what we will get is summation over Ej, let's say, okay, over K. There is no K here. I mean, I'm just saying, I'm just swallowed this one step. Okay, this is clear, I believe. You just write it, it's exercise, okay? Eik times ELJ is Ej. So whatever the K here, I mean, K and L, if they are different, that is 0. If they are equal, it is just going to get this. So that this will be n times summation Eij, the same thing you will get, n times the Pn. Okay, Pn equal to n times Pn. Sorry, P square equal to n times Pn. P square equal to n times Pn. So from that it is clear it's positive, right? Then Pn is equal to 1 by square root np times 1 by square root np, and P is self-adjoint, and it's positive. Okay? I mean, which is in the form of A star A or A square. Okay? So this is, so it's positive. Or you can see that there is another way of doing it. Pn square equal to n times Pn. So if lambda is an eigenvalue, we will use this later, value of Pn, then lambda times 1, I mean, lambda times 1 minus lambda equal to, no. It just says that n 1 minus lambda square minus n lambda equals 0. So lambda into lambda minus n equals 0. So lambda has to be either 0 or n. Okay. 0, n. So they are positive. So the eigenvalues are positive. So it's a positive number. So from that it follows. You only have to show that. Okay. So for 2 implies the n positive is implies this. We only have to show that this is positive. We have shown that this is positive. Okay. The next step is we assume 3 implies 4. 4 implies 1, we have already proved. Okay. 4 implies 1 is proved. Okay. We only have to need to prove 3 implies 4. Okay. 3 implies 4 is what only we need to prove. Okay. So this is we should do it carefully. That's all. This is also straightforward, but we have to do it carefully. So what we have is Pn equal to summation Ij equal to 1 to n Eij tensor Eij P of P, which is equal to 1 tensor phi of Pn, okay, equal to this phi of Eij, right? This is greater than or equal to 0 is what we have. As a matrix, this is greater than or equal to 0. Okay. So let's call 1 tensor phi of Pn as a, I have used the Pn there, everything. So I just, this may be confusing. This is okay. This is just a matrix. Okay. I mean, this phi is the small p, this is like, so this is a matrix which is greater than. Any positive matrix can be written like this. So this is I will just write it. Any positive matrix can be written as, any positive matrix A can be written as A is equal to summation B. So we need up to D. Okay, J equal to 1 to D VL B. Okay. The reason is if A is positive, so it can be written as summation lambda I Ti. Okay. In particular, you can repeat the lambda. This is with respect to distinct lambda. You can repeat the lambda. Then you can write it as I equal to 1 to n, lambda I En. Okay. This is the project is Ei. The projection onto the orthonormal basis. Where Ei is an orthonormal eigenbasis. Okay, is ONB. ONB eigenvectors. Okay. ONB eigenvectors. You can write Ei to be like this. Okay. Then you take only distinct, only non-zero lambda value where I equal to 1 to d. Let us say 1 to d where lambda I is strictly greater than 0. Okay. Equal to 0, you just forget it. That's an orthonormal basis, but we are taking only those EIs for which lambda I is greater than 0. Orthonormal. Okay. 0 means that that doesn't count. Now you just take this is positive, so you just have to count that. We take VEI to be lambda square root of lambda I EI. That's all. Okay. Then the VL you will get it. This is J. I'm sorry. This is J. Okay. Any positive matrix can be written like that. Okay. Now let us come to this. Now, in particular, that the script phi, what we have written, that can also be written like that. I'm erasing this theorem. Actually, that room has 4 boards, but it's occupied most of the time. Okay. Okay. Now phi is greater than 0, so phi is positive. So let phi equal to summation over j equal to 1 to b j b j. Okay. Where each vj is a vector in Cn So this is a matrix in Mn tensor mm. Okay. Phi is in Mn tensor mm. This is in mm tensor mm. So this should be, these are all n cross n matrices with entries coming from mm. So these vectors Vj should be Cn in Cm. Cn Cm. This is how Vj should be Cn cross Cm. Okay. This is what phi m is. So each Vj will look like it's a column vector from omega j1, omega j2. I mean, it's a nm vector. Okay, it's in Cnm, which is like this. So it will look like omega j n, right? Okay. Omega ji maybe in the middle. Omega ji, okay. Omega j n. Okay. It's a column vector. It will look like that. This is a Vj will look like. So now our Pn is summation Eij tensor Eij. Okay. Or our this phi n is going to be phi of Eij. Okay. This is our phi n is. Phi n look like this. Okay. So the ijth matrix of ijth, we haven't confused the representation. I mean, what the way we have written, okay? The order, everything we have maintained. Okay, so this Bj, this matrix, this whatever, is ijth entry, pnth ijth entry, which is a matrix, which is an m cross m matrix, is going to be ijth entry of this. Okay, ijth entry of this is going to be this, the so-called cross product of these two. So it is just going to be ijth entry of this is going to be w. I mean, sorry, not ij, ii prime. J I'm using there. I'm using j for this. So ii prime. Okay, ii prime entry is going to be. Let me just write it. Okay, j. Okay, omega j I prime entry. Okay, over summation over g. J is from 1 to j is from 1 to d, some d. Okay. I mean, you just Vj looks like this. Okay, Vj looks like this. Vi, Vj, Vi, I mean Vi the transpose. It will look like this because with the bar, all those things are taken into account. If you take star, that's all it is. It's like this. So if you just multiply these two things, you get a matrix. The ith entry of here, jth entry of here will come here for this. When you sum it, you get that. So phi nth ijth entry is this. Phi nth ijth entry is precisely phi of eij. Okay, so this implies phi of eij is exactly equal to this summation. So if you just think about a minute, it is just basically this omega. Here it is j. Here it is j. Okay, omega j. Sorry. See, I mean, I'm using I prime. Okay, not j. I'm using for something else. Omega j I. Omega j I. Okay, it's better you understand it clearly. There is no confusion. Okay. So phi I prime looks like this. Okay. Now we can calculate if you have a x in any x in M and C. I'm sorry, it is just any x in M and C. With x is equal to, of course, x will look like this, right? Xij, these are numbers. Eij. Okay. Okay. Xij are numbers. Any x in M and C will look like this, of course. Okay. See, right? That's cross product, I will get confused. So I'm writing Eij. Okay. X will look like this. So phi of x is going to be just the summation of that. Summation I. I'm sorry, I have to use I prime. Okay. J I'm using for something else. Sorry. I prime, which is going to be I prime of x's are scalar. It is just you get this one. Okay. So we know the value of this. So this is just I prime, then summation over j. Okay, and we know the value of that, which is just omega j I. And we get xij here. We get xij here. Okay, omega j I prime. Okay, that's what we get. Sum is over. There are three sums. Ij equal to 1 to n. This is 1 to m, right? M. This 1 to d. Sorry. J is from 1 to d. Ij is from 1 to n. D comes from the decomposition of that phi. Okay, that matrix phi. Okay. Okay. Now I can put this xij in the middle. Okay. I need both the boards. This is the problem. So I will write it here again and then easier. So what we have is, if you have any x which is equal to summation xij, eij, that is how any x will look like, then phi of x is equal to summation I prime e I prime. So any x will look like xi I prime. That is the duster. This is what we got it in the last. J equal to 1 to d, I and I prime equal to 1 to n. Okay. Then xij, we got xij, I put it in the middle, that's all. Omega ji xij. Then I just put the scalar in the middle. Okay. Omega ji. Okay. Just to multiply S matrices. Okay. Now I do the following. I define matrix Vi, Vj to be, see, these Vjs are same as those small Vjs. Vjs are nd vector, which you can write, nd vector, which you can write it as some d cross n vector. Okay. So actually I could have taken this d to be m. That's okay. I mean, because that's what the statement is. D to be m. It's okay. So Vj to be, we can write it as V. So now we want to m cross. So m cross this. Okay. So it will be, there are m of them. These are column vectors. So it will be, this will be a row vector. Omega j 1, omega j 1 up to omega j d. Okay. Okay. Here we get, of course, omega j here. Yeah, I doesn't matter. Okay. So this is a, I need n of them, right? Where did I write about omega j? Vj to be look like this in omega j, where each omega j, I mean, sorry, I'm unnecessarily confused. I'm sorry, I have to recall it. See, we are considering mn cross m equal to m here. Right? M equal to n. We are considering m equal to n. So this will be n only. Okay, this will be n only. So all these omega j, these are all Cn vectors only. Okay, the d comes here. Yeah, this phi map is from, I mean, we are taking mn tensor mn. Okay, this will be a this vector only. Okay. Okay. Vj is an n. Yeah, there are j of them. I think it's okay. Okay. Yeah, d is different. G is a sum. Sorry, we cannot take d equal to m. I said d equal to m. We cannot take. D is not equal to m. Are you getting lost? Is it getting messy? It's okay, no? It's all a simple thing only. It is just we have to write it carefully. Okay. So now these are all row vector. Okay, so there are d rows here. Okay. There is no d. This is just n. I'm sorry. Omega 1 up to omega n only we have. There is no d. Sorry. This is n only. D is the number of Vj's. So that has nothing to do with d. Okay. D is the number of G's. I'm sorry about it. Okay. So this is just omega j up to omega n only. Okay. Okay. Vj is this. Now, so these are all, these are all, of course, n cross n matrix, right? These are n cross n matrix. So if you take x and then this is capital Vj, okay? These are all n cross n matrix. Vj, Vj star. I just compute what is this. Okay. So we will have Vj star means we will have this. Okay. Omega j1 up to omega jn. Okay. And then the matrix x will be there. Okay. And then we are having this omega j1 up to omega jn. Okay. That's what we have. Okay. That is what Vj x, Vj star x Vj is. So this is each one is a this is a column vector. So there are n of them is there. This is a column vector, and you have just stacked it like this. Okay. Okay. Now we want to show that this is actually equal to. So if you sum it over, what we get. Okay. We have already proved that phi of Eij, we have a form like this. Phi of Eij is form like this. Okay. Now this is equal to summation. So this is just, we have x here. This is just going to be, I just claim this is just xij, xi I prime. Okay. Summation over xi I prime, omega ji, and then here it is the other way, omega j. Okay. It is just this vector. You just compute the matrix product. So here you are going to take the, if you want to compute, how to do that? So this is my claim. This is equal to this. So what I have to do is the following. I just write it like this: omega j1. I just write it like this, omega j1 up to omega jn, okay, and x, and then write it like this: omega j1 up to omega jn. Its kth entry has to be equal to this kth entry of this. Okay, kth, okay, has to be equal to this kth entry of this. So kth entry of this is this. That is just clear. This is just this. This is just a scalar. You can take it out. Okay, so you take the kth. You just have to take the kith entry of this, multiply with I prime entry of this, and you take the I prime L entry of this. That's what you will get, right? So which will be omega, whatever you have here, which will be the Lth entry will be, if you want, you just write it like each omega j will look like this, omega L I entry, right? So if we just consider the kth entry, they will be same as the kth entry of this. I leave it, it's clear. Okay, I leave it as an exercise, but it should be verified. It's just a matrix multiplication. It is just the Lth entry of this. So because of that, these two are equal. Okay. Now if you sum over j, you can sum over j. Okay, you can sum over j. It will be sum over j. Then you can interchange the sum. Okay, which is the summation I prime, and summation over j of the same thing. And we have proved that that is precisely, if we take the xij out, this is precisely the phi of eij. We have proved that in this board. Okay. So phi of eij. So this thing implies that clearly phi of x equal to summation over vj star x vj. J equal to 1. I think it's clear. Okay. So from this board, okay, we have proved that we have computed phi of eij equal to this. Okay. So if you have xij scalar, xij phi of scalar times this is xij times this. That is what that entry there is. Okay. That is what that entry here. Okay. You have the xij here. So because of that, it follows that phi of x is this. Okay. Okay. So that's what we wanted to prove. Okay. This Choi-Kraus theorem is proved. This is what is called, this representation is what is called Choi-Kraus representation. Okay. Choi-Kraus representation. And we have this matrix. So this is something different. Okay. This phi is the map. This script phi is the matrix. Okay. This is a positive matrix in Mn of Mn. Okay. Mn of MnC, positive matrix. Okay. This plus means positive matrices. Okay. Any algebra with a plus is positive element. Okay. This is a positive matrix. This is what is called Choi-Kraus, I think. Okay. Choi-Kraus matrix. If I am wrong, I will correct it next class. I think this is the name. Okay. This is the name. Of course, they must have considered this, they must have proved it. Okay. This is what is called Choi-Kraus representation, and this matrix is called this. Okay. Okay. So one thing is clear, this matrix completely determines the CP map. Okay. That is clear, right? So this is remark. This map phi going to, I should have used a different notation. I used this P for that thing. Let me call that thing as P phi. Okay, this is better. Okay? This is better. I'm sorry, I'm changing notation. This P phi is nothing but summation Eij tensor the phi of Eij, whatever. Eij. 1Tn, and this is in Mn of Mn. C plus. Okay. Is a bijection. It's a bijection, and it determines that. Okay. And I will orally tell you the proof. It's clear. Okay. First, it's a linear map, of course. I mean, phi going to, if you have lambda times phi, then you are just going to act phi here, so you are going to get lambda times that. So this is a bijection. Okay, I mean, this is all CP maps. Okay, this is all CP from confused somewhere. I'm sorry, there is a M everywhere. Yeah. I made a mistake in the last thing. I said that those things. We are considering that K equal to N, not M. M is not equal to N. There is a mistake, but I cannot correct the whole thing. So what we did is the following. We had, this is what I'm confusing. So we have M to MM. This is what our phi is. Okay. So this P phi, whatever this Pn is in Mn of Mn. Okay. Mn cross Mn, which is Mn tensor Mn. This whatever P phi we are defining, that is in Mn tensor Mm. Okay. So those VL is a vector in Cn tensor Cm. I said you can take M equal to N. That's not correct. I'm sorry. You cannot take M equal to N. So this VL looks like those omega 1 up to omega N, where each omega I is a vector in Cm. You cannot take Cm. Okay, Cm. So now, fortunately, the proof is here, so I can correct the mistake here. Okay. So here, these are all vectors. This omega Ji, this is a vector in Cm. Okay, these are all vectors in Cm. So these are all n thing. This is a n cross m matrix. This is a n cross m matrix. Okay, that is how it will work. So this is a n cross n matrix. This is a n cross m matrix. This is a m cross n matrix. So you'll get a m cross m matrix. So that's how it is. So everything, except that m equal to n, I said I bluffed something. So apart from that, everything is fine. So anyway, you better write the whole thing again. Better write it and verify this. This is important. Okay. Okay. So if we have a CP map, this is a map from all CP map from MNC to MMC, which is of course a vector space, which is just, which is not vector space. Sorry, you cannot multiply by a complex number and get a CP map. Okay, you can multiply by positive numbers. This is CP map, and that is to all those matrices in Mn tensor MM. Okay, positive matrix. Positive matrix. So if you have a CP map, you get a positive matrix, well defined like that. It is just, you are just taking that to be summation Eij tensor E of Eij. Okay. Okay. Summation over A equal to, which is positive by the property of the CP map equal to 1 to N. Okay. So if you have a CP map, you get a positive matrix there. And if the CP map is 0, then the matrix is 0, of course, clearly. Okay. On the other hand, if the matrix is 0, then the CP map is also 0. So suppose Vi star x Vi equal to 0. This is sum of positive matrices. They are 0 means each one has to be 0. That is because if this Ai equal to 0, sum of Ai, okay, for some Ai, A equal to 1 to N. These are all positive numbers, so you can take the sum outside, I equal to 1 to N. Okay, this is equal to 0 means each one is positive, so they have to be 0. So from that it follows. Okay, so it's 1, 1. Okay, so it's clearly 1, 1. This map is 1, 1, well defined. It's clearly well defined. 1, 1, and it's surjective. Given anything, you can go through the same way. You can define that. If you have any just this matrix, you can define taking this matrix row vectors and other. Matrix can be written like that, BL using that orthogonal. Using the decomposition, you can get something. Okay, and you can get something, and P phi of that is precisely that because it is defined through those matrix units Eij and other things. Okay, so you have to go through all that, and you can verify that. I would suggest you go through that. Okay, we will have it in the exam or something. So you better go through it. Okay, so this P phi, this is a bijection. P going to P phi is bijection. So the completely positive map is determined by this positive matrix. Okay, that is number one. Then we want to consider what is called a dual map. If phi is from M and C to M and C. Okay. Now M and C is an orthonormal basis with respect to the trace inner product. Okay. With respect to trace inner product, which is just AB equal to trace of A star B. This is the Hilbert space with respect to this trace inner product. Okay. So now it's well. So this is from M to M and C. So there exists a phi star adjoint, just same Hilbert space theory from MMC to MNC, okay, such that phi of such that we can compute the trace. This is the trace in trace of phi of where I want to get A phi of B. Okay, A phi of B. Instead of A, you can take A star or whatever, doesn't matter. So this is the trace in this is in M and C, where M P of B will land in MMC. A in MMC, B MMC, B in M, B in MNC. Okay. This is equal to trace of P star of A, okay, B. It is just the same property, adjoint property. Okay. Just I mean, you just consider the matrices as Hilbert space with respect to the trace Hilbert, which is an orthonormal basis. Okay. You know that that is exactly equal to the same as the Euclidean basis. You just write the n cross n matrix as a n square vector, and it is basically it's the same as the Euclidean usual Euclidean inner product. Okay. Okay. So if you have a phi, you get a phi star. Okay, like this. So notice P of, let's say, P is from MMC to MMC. Okay. Then one, if P equal to summation J equal to 1 to D, B J star P of X is equal to B J star X D J, then P star of Y is equal to summation J equal to 1 to D, Vj X Vj star. That's all. Okay. So this thing implies, from this it's clear, if phi is Cp is equivalent to saying phi star is Cp. Okay. Is the other way also. If this is given by this, then I mean phi star star is phi, of course. Okay, it's the same thing. Like, and third one, P is a quantum channel that is trace preserving, Cp and trace preserving. Cp and trace preserving, if and only if P star is Cp and unital. That is, P star of 1 is 1. Unital means it takes identity operator to identity operator. Okay. Proof. One, So we just have to use the definition of phi and phi star using trace. Okay. So notice that, I mean, I hope you know this generally. If I mean, in general, in any Hilbert space, if xy equal to x prime y for all y in the Hilbert space, then x equal to x prime. Okay, that's clear. You just take y equal, I mean, you just take x minus xy is equal to 0, then you take the inner product with itself, and you'll get it. So x equal to x prime. Okay. So we want to use that. Okay. Now trace of phi of, so phi comes the other way. So x phi of y equal to trace of x summation vi star x vi, sorry, vj star x vj equal to 1 to d, yeah, d. Okay. I hope you know this property. Trace of AB is equal to trace of BA. I mean, this is just matrix product which you can, I mean, trace of AB is what? Summation AB II, ith entry. So which is just going to be summation over A of ij, B of ji, summation over I and j. Summation over I, summation over j. You can interchange I and j. So this will be equal to, exactly equal to j and I. Okay. Summation over B, ji, A, ij. ij, I mean, it is just the same thing. So it is just the same thing. Okay, you can just directly verify that. Of course, this you can interchange because it's a finite sum. But if you want to prove this formula for the infinite dimensional, you have to consider first positive operator, some positive things. I mean, so that positive things you can, positive sum you can interchange. So you have to use that, and there are these problems. Okay. So trace AB equal to trace BA. Because of that, we can write it as, so you can take the summation. So trace AB equal to this, so but trace ABC, you cannot interchange it arbitrarily. You have to interchange only trace of, you can take one of them, BCA kind of thing you can do. You can take A here. You cannot write, it's not commutative kind of thing. You cannot interchange C and B here. You cannot do that. You can take this A here. Okay, so ABC is BC and A you can take. And then B you can take. Okay, you cannot interchange CB here, you cannot write it. Okay, we should remember that. It's not like commutativity. Okay, inside trace one after the, I mean, we can take it this way. That's all. Okay, so this is same as, so because of that, this is same as trace of you can bring this x bj x bj, this is y, no, sorry, y. Okay, vj, I can bring it here, vj x vj star y. Now you take the summation inside, and this is same as inner trace of, this is same as trace of I mean, summation j equal to 1 to d vj x vj star. Okay, the whole thing times y. Okay, so this precisely because from this identity, because this is an inner product, we are computing the inner product. So from this identity, it follows that phi star of x is equal to summation j equal to 1 to d vj x vj star. Okay, that's all. It just says that v1 up to vd determines phi, then v1 star up to vd star determines the phi star. That's all. Okay. 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 So from this, now we want to prove that phi is Cp is equal to trace preserving. It should follow from the definition. Phi is Cp. I mean, so now this implies if phi is Cp, phi star is Cp. That is clear. Phi is Cp means it is determined by some matrices v1 up to vd. Then you get the corresponding v1 star up to vd and define that. That gives phi star. Phi star is determined by that. So that is Cp. Similarly, if this is Cp, this is Cp. So that's clear. Now we have to prove that if phi is trace preserving, then phi star is unital. Okay. Phi is trace preserving. That is, trace of phi of x is equal to trace of x. This implies trace of phi of x is summation vi star x vi. Okay, trace of this. Okay. This is equal to, which is equal to trace of x. That is, trace of x is equal to this, right? Now this is equal to trace of x vi star, right? Okay. Now this is nothing but inner product of x vi star. Okay. Now that is equal to trace of x. That's what we say. So trace, that is just means that x inner product, or you can write it the other way. I just better take, you can take it vi star. This is the same thing. Okay. You can write it if you want. I take the vi that side. So trace of summation, trace of vi star x. So which is just inner product of summation vi star and x. Okay. Trace of x is just x, the inner product with x and identity. Okay. So 1 inner product with x. This 1 is on, I mean, this 1 is on MNC, right? MNC. Okay. 1 is on MNC, right? Okay. Inner product with x is same as vi is an operator from Mn to MNC. So vi star is from Mn to Mn, Mn to M. So this is n cross n. Okay. This is an n cross n. Okay. So this is same as summation vi star. Okay. J or J, I think it's J. Okay. I equal to 1 to D. I use the J usually. I use the I. Okay. Inner product x. But this is for all x, right? Okay. So this implies summation over j equal to 1 to t, vi star equal to 1. Okay. So if it is trace preserving, then this is equal to 1. Okay. But this implies, summation j equal to 1 to d, vi x vi star. Okay. Equal to phi star of x. Okay. This is the definition of phi star of x. So this implies phi star of 1 is 1, of course. Phi star of 1 m in MMC the same as m. Okay. Okay. I mean, you just insert 1 here. You just because it is trace preserving, then the condition is that implies that summation vi star equal to 1. From that it follows. Okay. Okay. Shall I stop or continue for some more time? Maybe I will recall this. Shall I continue? Okay, for a few minutes. Okay. Yeah, that will be a good point to end this. Okay. So we approved this. Okay. If a phi is trace preserving, if and only if phi star, the adjoint is unital. Adjoint takes identity to identity. So definition. So if P equal to summation Vi x Vi star, I equal to 1 to D or J. Okay. j equal to 1 to d. Okay. Then the minimum number of bj's required for this is what is called the Choi rank of this. Okay. T, which we denoted by CR, okay, of phi equal to minimum of d, such that summation dj into 1 to d. I mean, VIs may be different or whatever. We get a collection of VIs. Okay. For example, if they are linearly independent, then that will be the minimum, right? We can see that. You'll see that VI x phi of x equal to VI x VI star. Okay, that is what is called the rank of Choi rank of this map phi. Okay. Okay. So now the theorem is proposition is the Choi rank of phi is exactly equal to, you brought something. Yeah, a rat or something came with you inside. You open. Okay, that is equal to rank of that PV. But what it has to go out. It's a squirrel. Okay, poor guy. How will it go? Okay, let's see. Okay, I mean, squirrel may not bite all the wires. I'm worried about these wires. Okay. Okay. So we have, if we have a CP map, then we define the Choi rank to be the minimum of these D's required to this. Now we have a operator. We have a matrix P phi. The Choi rank of phi is same as the rank of P phi. That's what we want to say. Okay. Okay. Proof of this. First, we consider rank of P. Well, we have P phi. Okay. Rank of, I mean, this we defined our phi. We got back our phi. Okay, we got back. We have P phi. We wrote P phi like this, right? Summation j equal to 1 to some L. Okay. The D will come back such that Vj, right? Initially, we wrote our P phi like this. Okay. And it is precisely that L which occurs in that, in the proof. So from earlier proof, the Choi rank of phi, which is the number of elements here by definition, that will be L. Okay, that is a minimum, so that is less than or equal to L. But this L is less than or equal to rank of P phi, right? Or exactly equal to that. Okay, these are all those eigen vectors for which the eigenvalue is positive. That's how we define, right? So the rank will be exactly equal to that. So this is equal to rank of this. So this is precisely equal to that. So the Choi rank is less than the rank of P phi. So we have to prove the other way only. Okay. Well, processor fell down. You have to come and take it. Last time I took it and I got into a problem. Yes, thank you. Okay. So the rank of the operator P phi is less than this. Now we consider the following. Our phi of x, phi of x equal to summation Now we want to prove the other way. Okay? The number of element is less than that. Okay? So, okay. Now let some arbitrary thing. Okay? Let uh, uh, this is some arbitrary. Okay, j equal to 1 to d vl x vj x vj star. It does not come from pv. Let it be some arbitrary. Okay? For some or any v1 up to vd. Okay? Arbitrary thing. So in particular, phi of that pn, the pn is that, you remember, pn equal to summation yj eij tensor eij. Okay, it is at pn. So p of pn will be summation j equal to 1 to d vj pn vj star. Okay, correct? Okay, okay, by definition. Okay, okay, fine. Now we want to consider this d basically. Now this is nothing but this is exactly equal to this v1 up to vd. This thing is exactly equal to v1 up to vd, the diagonal matrix, times pn pn is an n cross n matrix, right? How can it be? So we have to prove that this, I mean, when we have this, we have to prove that D is less than the rank of P of N. That's what we want to prove. Okay. Now rank of, how we want to prove that? Let me write it and I will get the idea. I forgot the idea. Okay. We want rank of, we want the other way. Rank of P phi is less than or equal to rank of, sorry, the D. That's what we want to prove. Okay, rank of D. Now we want to write as D elements. That's right. So I want to write it as this is equal to, this is okay, I think. Vj's are, this is okay. V1 up to Vj. Okay. Diagonal. It's just diagonal Vj's. Okay. And Pn oh, I don't need to write. Sorry, it's all not needed. Okay, I mean, okay. Now let's consider this. Okay, we want to consider this is P of En. I mean, this is what our P phi, right? This is what P phi. Okay, rank of this is what rank of P phi is equal to rank of Vj summation. It's just immediate. Sorry, you don't need to write like that. Okay, D Vj Pn Vj star. Okay. This one tensor? No. This is Eij tensor Eij. Summation Eij tensor. Not one tensor. Pn. This is one tensor. You are right. Yeah, correct. Sometime I make a mistake. Yeah, this one tensor phi. This one tensor. You are right. Sorry. Yeah, correct. Sorry, it is one tensor. You are right. This one tensor phi, which is going to look like this. Okay. So, you are right. Yeah, now I think it's correct. Yeah, right. Sorry. Okay, maybe that's a mistake. So, okay, now let me write it. Want to prove rank of P phi is less than or equal to D. That's what we want to prove. Okay. Now, P phi is just, you are right. One tensor phi of Pn. Okay, Pn. So, that's right. So, that is just summation Eij tensor phi of Eij. Okay, correct? Now, this is okay. Yeah, you are right. Phi of Eij. And that is equal to summation over Ij, Eij tensor summation j equal to 1 to d Vj, okay, Vij, Vj star. Okay. This is okay. Now you can take this sum out. This is equal to summation Ij equal to 1 to, sorry, I take the sum j sum out. Okay. Summation j equal to 1 to d. Okay. Summation Ij, Eij tensor Vj, Eij, Vj star. It is just that matrix with entries Eij. This is just this is just, you know what is this matrix? This is just the Eij matrix. I mean, this is, you understand? This is its ith entry is this. Okay. So this is just, going to be V1 up to Vd. Okay. Then you have that matrix. Okay. You have that, just that Eij matrix. Okay. Eij matrix times, maybe this is star. Okay. I think there is star here. Sorry, this is star. This is star. There is no star here. Doesn't matter. Okay, we will have one of them. Star here. Eij. It is just the Eij matrix here. That Eij matrix is nothing but just Pn, right? Matrix with Eij is just Pn. This is correct. So now a V1 up to Vd. This is diagonal V1 up to Vd. This is diagonal up to V1 up to Vd. In the middle, you have Pn. Okay. This is what is P phi is. P phi looks like this. Yeah, this okay. P phi looks like this. Okay. So this implies rank of P phi is less than or equal to there is a sum. No, this is wrong. I'm sorry. This is not correct. Sum of that. Sorry, this is equal to sum of j equal to 1 to d. This is just Vj, only Vj. It's just a not diagonal matrix. It's like an identity matrix. All diagonal having the same entry. Okay. Times Pn times Vj up to Vj. Okay. I'm sorry, this is the right one. If you just multiply, you get that. Okay. So this rank of phi is less than rank of sum of matrices is less than or equal to sum of rank of this individual matrices. So this is equal to less than or equal to sum of rank of this matrix. Okay. Sum of rank of that Vj, Pn, Vj star. Of course, rank of ABC is less than or equal to rank of B. Rank is just the dimension of the range. Okay. So, I mean, should I prove that? I mean, rank of ABC is less than or equal to rank of B. ABC are matrices. Rank is the dimension of the range. Okay. So, rank of something is less than or equal to the image of that. Then you can remove the other image. I mean, any matrices take the dimension less than that. It cannot increase the dimension. Okay, so because of that, so usual linear algebra, this is less than or equal to summation over j equal to 1 to d rank of Pn. Okay, so it is just the d times rank of Pn. Rank of Pn is same thing is coming. It is a d times rank of Pn. What is rank of Pn? Rank of Pn is 1. All I have to prove is rank of Pn is 1. Okay. That is clear, no? Pn satisfies. I confused a lot. I'm sorry. Now all we need to prove is rank of this Pn, not P phi. The Pn is 1. Pn, you know that Pn satisfies this. P square, Pn square equal to Np. Okay. So it satisfies if lambda is an eigenvalue. Value of P, then it satisfies lambda square minus n lambda equal to 0, lambda into lambda minus n equal to 0. It satisfies this equation. So lambda equal to 0 or n. Yeah. Now if lambda 1 up to lambda, there are n square of them, eigenvalues. Maybe it's repeated, okay? Maybe we can repeat the eigenvalues. Lambda 1 up to lambda n square are the eigenvalues of P. Okay? Then summation lambda I equal to 1 to n square equal to trace of this. Okay? Trace of Pn. Okay? But the other hand, trace of Pn has to be n. Trace of Pn has to be n. Why is it n? That is because, I mean, you can directly calculate what is trace of Pn equal to, it is just what is Pn? Pn is just Eijth matrix at the Eijth level. Trace is just the trace of all those Eii, a summation of trace of Eii, basically. This is 1. So this is equal to n. I equal to 1 to n1. Pn is a Eijth matrix in each level. Okay. Trace is just the sum of the diagonal trace of the diagonals. All the diagonals are Eii. There are n of them. And each one has rank 1. So the rank of this is n. So the trace of Pn is n. And one of the eigenvalues is n. The sum of the eigenvalues is just the trace. So there should be only one non-zero eigenvalue. Okay. So this implies there exists only one, of course it should exist, okay, one non-zero eigenvalue. Eigenvalue for Pn. So this implies rank of Pn equal to 1. This implies rank of Pn is 1. Okay. So rank of Pn is 1, also everything follows. Okay. So this is implies the Choi rank, the number of D is exactly the rank of this. Okay.